started.
Okay, guys, physical properties, polarities. See where we left off at? H2O polar, CO2 with nonpolar, SO2. You get a Lewis structure for SO2. Got to have a structure before you judge polarity. Most dipoles may or may not cancel out. SO2. Real quickly, number of valence electrons, systematic approach put together. Anybody get a structure? I'm just going to put something up here quickly. How about that there? Lone pairs we can put there, yeah. Does this seem reasonable structure? I'm not going to do it systematically. Oxygen has an octet. Sulfur, 2, 4, 6, 8. Oh, 10 electrons around sulfur. Can you do that? No. Yes. Okay. Could have drawn a resonance structure. You could have, well, systematically, boom, boom, electrons here, electrons here. How many total valence electrons should be 6 times 3 is 18. 2, 4, 6, 8, 10, 12, 14, 16. There's only 16. Where do we want to put the other lone pair? Yes, sulfur. Can't put any more on oxygen. So there we go. You can just, sulfur still doesn't have an octet, does it? 2, 4, 6. So let's bond here. This is going to be resonance structure because we're only moving pi electrons. That's actually pi electrons if you think about it. So now we got double bond, one lone pair, oxygen. Here, sulfur have an octet now. 2, 4, 6, 8. Yes. Minus, positive. That structure would work too. Or you can take these and move them in, and that would give this resonance structure if you move them in. That's okay. Now everything's neutral. Sulfur does have an expanded octet. Either one works because any resonance structure has the same hybridization, geometry, everything. You can work with either one. Here, okay, dipole, sulfur, oxygen, oxygen more electronegative. By the way, how are these three things going to be spread out on the sulfur? Sulfur is a little bit unique because it has d orbitals and that can change the hybridization discussion. But simply three things, trigonoplanar. These are not linear. Do these cancel each other? No. No, they do not. You actually have a conflict here. You have electrons here, but the dipole is going this way, actually. These do not cancel, so it's polar. Polar. CO2 is nonpolar, SO2 polar. Dipoles sum up to give a net molecular dipole. Again, even though there's electrons here, it's a little counterintuitive that this would be the high electron region. That could be more discussion. Carbon tetrachloride. Carbon with 4, what's the hybridization of the carbon? Tetrahedral, yes. 2 in the plane, 1 forward, and 1 back. Okay. 4 individual dipoles, all identical. Do they cancel? Yes, they actually do. Carbon with 4 identical things, they actually do. You got 3 chlorines. If we hold it like this, the tetrahedral, okay, 2 in the plane, 1 forward, 1 back. If you hold it like this, though, these 3 chlorines are each pulling downward, but not straight down. They're sort of pulling a little bit to the side. But that's 3. Those sum up to have 1 kind of straight down. And that 1 straight down is canceled by the 1 straight up, if you sum them all up, because this is a third here, but the third equals sort of a hole this way, and then a hole that way. Okay, so they do cancel. Four equal things on a tetrahedral are going to cancel. Carbon tetrachloride is a nonpolar molecule. There's no net molecular dipole. No dipole moment. What about CHCl3. Anybody know the name of that compound? You could call it trichloromethane. You could call this tetrachloromethane, but usually it's called carbon tetrachloride. Carbon trichloride, maybe? That's odd. Trichloromethane, but nobody calls it chloroform. Okay? That's chloroform. Queen Elizabeth took it during childbirth as anesthesia. That started that. So basically, I'm just going to erase this here, put an H. Okay? What do you expect here? Okay, H. 3 chlorines pulling straight down. Is the H going, is that going to cancel it? No. No. And so you're going to have a dipole. By the way, the CH is considered nonpolar. CH, always just nonpolar. Forget about it. Nothing here. 3 chlorines straight down, summing up to have 1 molecular dipole straight down. How would you show that through here? It's a little bit difficult in a 2-dimensional drawing. Right? It's much easier to see it here, yeah? It's straight this way. Leaving this up here partial positive. It might be easier if we redrew this a little bit differently. I'm not going to take the time, but something illustrated, you got to look out for 3Ds. I kind of got this chlorine kind of jutted up. If I redrew it, maybe more like this. And maybe if I redrew, you know, you could maybe try to make it. But then it's sort of straight down through there, and then I don't know how you're going to draw the. That's in the plane, sort of straight down. You kind of got to get a little handle on that. But it is a polar molecule. What about dichloromethane? Dichloromethane. So if we had 2 hydrogens, yeah, 2 chlorines, 1 pulling here, 1 pulling here. Again, a net dipole straight down. Not going to be canceled by anything going this way. Okay. We might be able to show this. If we show the 2 chlorines in the plane, and then maybe show 1 H like this and 1 H like this. That's a little bit, any drawing I would have to sort of look at and say, is it a good representation? But in the end, the dipole, we can draw it, it's coming straight down between the 2 chlorines. The 2 chlorines, okay. Problem is, these look like they're to the side up here. Really, 1 H is coming straight forward, and the other H is going straight back. If you want to make the chlorines green, and then the dipole is straight down. So that needs a little bit, maybe fixing to illustrate that. Having at least 1 tetrahedral carbon to sort of look at as you look at things in your textbook, or to see it more in your hand, would be helpful as you're learning this. Trying to manipulate these structures. So, chloroform, dichloromethane, polar. Those 3 there are very common halogenated solvents. Although these tend to be toxic, a little less toxic. Dichloromethane is a common solvent in the laboratory. We'll see a list of solvents on one of the next pages. So we mentioned sodium chloride, something like that. It's not covalent, never was. That's the extreme. That's where, even if it started out like that, the chlorine is so electronegative, it just, instead of just pulling, it just takes. So it just takes the electrons and it exists like this. So that's just the extreme. Okay, some physical properties. Boiling point and melting point, which, by the way, next week you'll be doing both of those in lab. You'll be doing a distillation. There's a demo of the distillation on the YouTube page. Okay, please watch that. Of course, this week in lab, you're doing some solubility. Okay, boiling point. To get a compound to boil or to vaporize, we must overcome all intermolecular attractions, which hold the molecules together. Okay? If I have molecules in a flask or something, they're interacting with each other by some type of intermolecular forces, IMFs. We need to know what types of IMFs are possible, the relative strength of those IMFs. That's going to be very important in predicting boiling point. The stronger the IMFs, the more energy you're going to have to put in to break the interactions. Not the covalent bonds, IMFs, which are sometimes called non-covalent interactions. Okay? Like you guys, if you're each an individual molecule, you're not just sitting there minding your own business, right? You're kind of connecting with neighbor, maybe even holding hands with neighbors. Not covalently, but some type of interaction. Maybe you're holding hands and feet and hugging. That would be a very strong IMF, level of IMF, right? You have to be able to assess that. Okay. Higher IMFs, higher boiling point. Types of IMFs possible. They're listed there and they're ranked in order from weakest to strongest. Now we can also use the term polarity because a weak IMF is going to come from weak polarity. Strong polarity is going to lead to stronger IMFs. So you can essentially say that's just a ranking of polarity. Okay, number one, right here. Number one, van der Waals attractions. Sometimes called London dispersion forces. I don't really distinguish between the two. Pretty weak. Let's look at some examples here. Look at these hydrocarbons. Saturated hydrocarbons, right? All right, no pi bonds. What we got here? Propane. Propane, a gas at room temperature, boiling point -4. Propane using your gas grill. Right? What is this? 1, 2, 3, 4, 5. What we got there?
Pentane.
Pentane. Yeah. Boiling point is higher. Okay. Pentane is a liquid at room temperature. Then we go over here. You should name this compound. How many carbons? 5. So it's a constitutional isomer of pentane. Same formula. This, the boiling point actually dropped. Why is it lower than pentane? It's back down to a gas at room temperature.
Because it's branched?
Yes, because it's branched. Okay. What type of polarity or IMF possibility do alkanes have? The only thing they have is van der Waals attraction. Van der Waals is a weak temporary dipole induced by molecular contact. Okay? Very weak. But when molecules come into contact with each other, and I approach you, two molecules, what's on the outer skin of the molecule? Skin, outer side. Electrons. Okay? The nucleus is more in the middle. The electrons. And so you've got outer electrons, and when these electrons bump into each other, what happens to the electrons? They become sort of perturbed, or they respond, go negatives and negatives. They're like, whoa, hold on, a little bit interaction. It causes the electrons to sort of distort, to be perturbed, whatever kind of term you want, okay? And that perturbation causes a fleeting, temporarily dipole. Okay, it's a little bit nebulous, but if the electrons sort of move, it sort of creates a little partial positive area and a partial negative area, because the electrons became a little asymmetrical in their positioning. Okay. Now in physics, you'll see this consequence of this. I think in physics, some of the faculty will take a balloon and rub it, and then it'll stick to the wall. Because the rubbing, the friction, the mechanical motion is making molecules come together, and they're perturbing the electrons a lot, and they create a situation that it will kind of then, it became polarized. This is very weak though. And this is what's getting at the idea of van der Waals attractions, this type of IMF. That's all hydrocarbons have, because they don't have that's slang. They don't have any permanent dipole. All they have is this induced dipole. Induced, that's actually a common term, induced dipole. Now, which one's going to have more of this? Kind of makes sense. The more surface area the molecule has, the more induced polarity it will have as a result of this. So surface area. Which has more surface area, propane or pentane?
Pentane.
Pentane has more surface area. So there's more electrons doing this, and you get more of this kind of stickiness due to this fleeting dipole stuff. More attraction to the molecules. Higher boiling point, because you've got to put in more heat to overcome this stickiness that's created. Okay? What about this? So that's why that was higher than that one. Why is this one then lower than this one? They have the same number of carbons, they're isomers. This one, the surface area is decreased because this carbon in the center is sort of buried in the middle. So it doesn't really as much influence the outer, you know, you can argue some, but it's kind of buried in there. And so it has less surface area, and thus it has less of this induced dipole capability. All right, and the boiling point is going back down. Take home. How do you recognize buried in the center? Branching. Whenever your hydrocarbon or your molecule is branched like this, instead of linear, these are linear alkanes. Branching is going to lower the boiling point because they have less surface area, because branching creates these hidden atoms in the middle. Okay? Now, usually we'll have something written over there, and I'm going to reread it to you. I basically told you in my own words, then you can read the written words. All right, next. What was number 2? I'm thinking it was probably dipole-dipole. What was it? Dipole-dipole? Because that looks like what this is. Let's look at this series here. 1, 2, pentane 36. Yeah? What functional group here? Ketone. Ketone. This ketone has a higher boiling point. Very similar, number of carbons, thus very similar surface area. All three of these have similar surface area. Both of these are much higher than this. Why? Well, because both of these actually have permanent dipoles, right? No permanent dipole. Only induced dipole. That's all it has. Now when two molecules that have permanent dipoles come together, boom. My positive, show me your negative. Boom. We can attract real good, positive and negative. And this is stronger than this fleeting weak van der Waals. Permanent dipoles lead to greater IMFs. Poor little guy, don't have much going on for it. Lower boiling point. Of course, it's higher than methane. What's the boiling point of just one carbon, methane? Like -100. I mean, it's a super low boiling point. It hardly has any van der Waals. At least this has got some van der Waals. So, polarity. And this is illustrating, instead of elbows here, this is more of a chemical, an illustration. The partial negative of the oxygen interacting with the partial positive of the carbon. The dash just sort of showing a non-covalent interaction. Okay? And you can sort of illustrate how all your molecules would be sort of holding hands a little bit. That's a stronger IMF than the one above. Okay, third one probably was hydrogen bonding. Look at these two. This alcohol has a higher boiling point than this alkyl chloride. By a substantial bit. What's that, about 40 degrees? Why?
Because the hydrogen is so much more positive because of the oxygen being so electronegative that it's even more attracted to each other. Another electronegative.
Yeah. And what you're describing is yes, hydrogen bonding. We'll get at it. Yes. Okay, what is hydrogen bonding? Hydrogen bonding is actually the same as number 2. It's a permanent dipole situation, but it's a special number 2 that only occurs with certain atoms. And with certain atoms, it's particularly strong. And because it's particularly strong, it gets its own name, and it's called hydrogen bonding. It's essentially a type of number 2, the dipole. Okay? That is the OH. Let's draw the H bond out, okay? But we have what? Partial minus, partial plus, right? Well, same thing here. Partial plus, partial minus. Both have permanent dipoles. But this one is stronger, and it's going to be called hydrogen bonding because it involves the hydrogen. Okay, it's a particularly strong dipole interaction that occurs between what? Well, you got to have the hydrogen, and the hydrogen must be on an O, N, or F. Because these are your 3 most electronegative atoms. This creates the most partial plus, okay, I'm drawing this big, most partial plus on the hydrogen. And this is called your H bond donor. The donor supplies the H of the scenario. So this is an H bond donor. It's partial positive because it's on the oxygen. Now what would be attracted to? A partial positive is attracted to what?
Partial negative.
Partial negative. So again, you've got to have a partial negative. Partial negative is going to be an atom. Up here, it's O or Cl. But actually, for hydrogen bonding, it's only going to be O. O, N, or F. And the interaction specifically is the lone pair, really, of an O, N, or F. Chlorine here is just not quite electronegative enough to be classified as hydrogen bonding. Yes, it's polarity here. But only when it's these do you call it hydrogen bonding, which implies only with these is it's stronger. These are called your hydrogen bonding acceptors. So, that is, this compound can do hydrogen bonding with itself. What does it take to do hydrogen bonding? You got to have a donor and an acceptor. Can this compound hydrogen bond with itself?
No.
Does it have a donor? No. It don't have a donor. Does it have an acceptor? It don't have neither. It can't do hydrogen bonding, so it can't do the stronger thing. It can only do the standard dipole-dipole. Okay, now you can show your H bonding interactions just like we showed on the previous page. Here's one alcohol. The H is partial plus because of that dipole. It would be interacting non-covalently with the oxygen of another alcohol. So there's your hydrogen bonding. But the H of that alcohol can be interacting non-covalently with the oxygen of another one. And so all your molecules are holding hands, but it's like a real good hold, a double hold with hand, just a stronger hydrogen bond. Okay, some questions here, and then we'll see what type of questions you have. Ether. Can this ether hydrogen bond to itself?
No.
You're all in ether.
You're an ether, you're an ether,
Can you all hydrogen bond to each other?
There's no hydrogen.
Why not?
Does hydrogen on
Does it have a hydrogen
on the oxygen?
acceptor? H-bond acceptor?
Yeah.
Yes, it does. Does it have a donor?
No.
So you got to have both. It's kind of like Velcro. You ever use Velcro? Yeah, right? You got to have the fuzzy part and then the kind of loopy part. Just helps you stick them together. What if you had just two of the fuzzy parts? They don't stick together. You got to have the donor and the acceptor, right? All right. So it cannot hydrogen bond to itself. Can it? But hold on. What about something else? Can this hydrogen bond to water?
Yes.
If it did, what would the hydrogen bonding sort of arrangement or network look like? This would be the H bond acceptor, and the H of water would be the donor. Because the H of water is on an oxygen, which to be a donor, you have to be on an O, N, or F. By the way, if it's on an F, it's hard to be anything else because that's just a complete molecule. How many H-bond acceptors and donors are present in the antidepressant effexor? How many acceptors? First, let's do donors because that's actually a little easier and the other has to be clarified. How many donors?
One.
One. Right? So one. Okay, all the other H's are on carbon. Okay, how many acceptors?
Two.
4.
2, 3, 4, and 5. Who wants to?
Can a donor also be an acceptor if it's lost? H. So the alcohol group would be
Well,
O's.
look over here. What do you mean, can a donor also be an acceptor?
But OH is a donor on effexor. But like, would you also consider that the acceptor because it lost?
Okay, well look over here and see if you can get your answer. Here's an alcohol with an OH. Is it able to do both?
Yeah.
The oxygen is acting as a acceptor and coordinating with the H over there. But the H on that oxygen
It's going to do the
is
same.
acting as the donor. So what's your answer? Yes. Okay. Here's where the clarification is. Again, how many? How many acceptors? 3. Anybody have a different answer?
What about the nitrogen?
Are you not counting the nitrogen? She said 3 and she's counting the nitrogen. So what's your answer?
I said 4.
4. Okay. Who says 5? Why? Because you're looking at long pairs. Okay. I like 3 or 5. I'd like to hear maybe why you're thinking 4. But here's where you need clarification. Is it just is oxygen 1 acceptor, or since it has 2 lone pairs, is it 2?
2.
You were counting it as 1. Okay. But it's got 2 lone pairs. So is it conceivable that it could maybe this lone pair, because it's really the lone pair that's coordinating, and then this one, you know, maybe. So is it 1 or 2? That's where the little ambiguity comes in. I would probably call it 3, with each atom being considered an acceptor. I could go with the argument of being 5, because there's really 5 lone pairs on these O, N, or F. Here's a take-home. I'm not going to trick you on this. It's okay. Some people say tomato, some people say tomato, some people say amide, some people say amide. All right. Bigger thing is, can you understand the 2 different arguments? Let's see what's below. Explain these. These are constitutional isomers, same formula. Why has this one got a much higher boiling point? This one's a liquid at room temperature, this one's a gas. Why is that higher? Hydrogen bond. Hydrogen bonding to itself. Usually when you talk about a boiling point, the compound is, you're assuming maybe the compound is pure, or when it's boiling, it's pure. And so it hydrogen bonds to itself. Can that hydrogen bond to itself? No. You've got to be careful. It can hydrogen bond to maybe some type of solvent. If you somehow bring in a H-bond donor to go with that itself. Okay, why is this compound a higher boiling point to this one? They're isomers.
Hydrogen bonding.
Hydrogen bonding. This one can't hydrogen bond to itself. Why is water higher boiling than H2S?
Hydrogen bonding.
Hydrogen bonding. Look at it. Huge difference. Is there no polarity here? Yeah, but it's not as strong as this. This is a particularly strong. It's huge. That's a 106-degree difference in boiling point. How else are you going to explain that? Actually, the H2S has more surface area because sulfur is bigger. So surface area got trumped by hydrogen bonding. As we go down, the stronger ones are the ones you want to consider first. Those are the ones that are going to win out. Okay, down here, again, methane. I showed you methane earlier. I mean, you know, there's no polarity here. There's no
Non-polar bonds.
How about this? This is an H here, right? Very similar in terms of surface area, but this guy has lots of hydrogen bonding. Lots. These molecules are going to be sort of not only holding hands and holding feet. Okay, 200 degrees difference. Yes.
Okay, do we need to be able to differentiate the one that's 48 degrees Celsius, the one that's circled, and then water? Do we need to be able to tell that just looking at it that water would have the higher boiling point?
We're starting to compare apples and oranges. It gets a little bit more difficult.
Okay.
I'm afraid to just say no. What there would be reasonable to kind of know. I'm not quickly seeing anything that's reasonable. That's an apples and oranges comparison. We'll try not to do that along the way as much because it can become more difficult. We have not distinguished between an NH hydrogen bond and an OH hydrogen bond. We classify them the same. Although maybe OH is stronger, but I'm not going to get into that detail.
So the number of possible hydrogen bonds increases the boiling point?
Yes, because if you just, for example, I could put another one up here. If we just had propanol with like a carbon on the end instead of another OH, this has a boiling point of about 100.
Versus the 197 with 2.
Versus 200, yes. More hydrogen bonding, it's like, okay, this is one hydrogen bond. Well, now let's make another. And now let's make another. And before you know it, it's like this. And you're going to have to put a lot of energy in to break those non-covalent interactions. A lot of applications to anything we do. I'll show you some along the way. Some I will just be expecting you to maybe look at on your own in the handout. Why do I include them? Because they're important. What holds DNA together? DNA helix.
Hydrogen bonding.
Yes, take a look at it. Okay, you got to be careful. Sometimes sort of non-chemists or chemists that did not do well in their courses will draw structures that are a little bit suspect. If you ever see anything, just ask. One of these has maybe an issue. I don't know if it's this one. Okay. Next, ionic attraction. This is going to be your strongest. Here, instead of just sort of a A dipole that creates a permanent partial charge. Here we're going to have full formal charge. And a full formal charge is even a greater charge, and that's going to lead to even a greater charge attraction. Greater IMF. Strongest. Okay. Look at here. For example, ethanol has a boiling point of 78. If we can make the ion, a saltier ion pair and be very ionic, formal charges, not just partial charge, which we call hydrogen bonding, full formal charges, higher IMFs, not only between these, but as you learned in Gen Chem, you get this kind of unit cell where all these charges are kind of coordinating together. So it's multiple molecules. But the boiling point of something like this is 500, greater than 500 degrees. Basically, most of these you're going to have a hard time boiling them. Okay? Thus, we'll get to solids, but usually these are solids at room temperature. We'll get to melting point next. Yes, melting point. Let's move on to that. With melting point, it's similar arguments. We're still looking at IMFs. You must overcome IMFs for the compound to melt. Because in the solid state, the molecules have a great interaction. And it's also a very uniform interaction. When you go to liquid, the interactions decrease a little bit, and the molecules start being able to sort of move a little bit more, even though there's still some flow. And you can look into how people describe liquids versus solids. But to melt, you do have to overcome some interactions, but you don't overcome all of them until you go to the gaseous state. Similar arguments throughout. Let's see if we can apply what we saw in the previous pages. One of these has a melting point of 126, one has a melting point of 44. Which is which? Which is a higher melter? It's this one. Why? Hydrogen bonding, because you can imagine the H on the end interacting with what? How would you show hydrogen bonding interactions here? Okay, have another molecule. Okay, what could the H interact with? It actually interacted with the O. Okay, NH of one molecule, hydrogen bonding to the oxygen of another. So that could be a hydrogen bond that you can maybe show. Okay, can this hydrogen bond to itself? Well, we got an acceptor there. We can also call the nitrogen an acceptor. But where's the donor? There ain't no donor. So you don't have the two parts of the Velcro. You only got one part. It can't do hydrogen bonding, so the IMFs are lower. This one's 44, this one's 126. Although, actually, this one has more surface area. Again, that doesn't win out. The stronger thing wins out.
So you know a nitrogen on the right still have 3 bonds and 1 lone pair, right?
And both of these, that's the case, yes. Three bonds, 1 lone pair.
So how is it still considered an acceptor even
But
if it only likes to make?
it's a lone pair.
Yeah.
But these are non-covalent interactions. Non-covalent bonds. By the way, nitrogen can have 4 bonds, but that just would not be the standard common for a typical state. Okay. So, the argument's the same as boiling point. You're just looking at melt. All right? On the one my agent keeps calling at 8:30. Yes.
That lone pair on that nitrogen in the second compound, does that lone pair get conjugated into the pi bond?
It is, yes.
So is it still an acceptor?
Very good question. Very good question. I haven't distinguished between that yet. Yes, it's going to be a fairly weak hydrogen bond acceptor because it's busy doing conjugation. when we get to acid base, we'll say that that's going to be a very weak base, which is analogous, same thing, very weak hydrogen bonding, except. So if you were asked to count them, you would have to say, is it or isn't it? You get into a little gray area, and it becomes. But guess what? A lot of science is gray area where it's just not an answer. You're more expected to be able to discuss the options and to say, hey, I don't think that's going to be a great acceptor because of this and that. Solubility. Okay. We're moving ahead, guys. Like dissolves like. That's a starting point. A compound will dissolve best in a solvent with similar IMFs. That is, a compound with similar polarity. That's what that really means. Because if you have very strong IMFs, that means you're very polar because, for example, hydrogen bonding or even ionic. Ionics are not typically liquid solvents because they're not typically liquids. But guess what? You do have a branch of chemistry known as ionic liquids. They're specialized. But that's okay. Question. Let's get straight to an example. Which amide, these are amides, right? Which amide above is most soluble in water?
First one.
Why the first one?
That's hydrogen bonding.
Can this not hydrogen bond to water?
Yeah.
It can. The acceptors.
Yes, it can. Maybe even the nitrogen. So why did you choose this one?
It
Because
has
it
more
has donors
intermolecular
and
forces, so it's more soluble.
More hydrogen bonding. Yes. You can do the same thing there, but then you can also maybe something like this. The donor and acceptor like this. More hydrogen bonding potential capability is what you got to recognize and say, it's going to be able to interact more with water, so I predict that one to be more soluble. That one to be less soluble. Now, question, is this compound soluble in water? That's a different type of question. Our original was a relative comparison. That's often easier. More soluble. Is it soluble in water is an absolute question, which is more difficult. I doubt it is, especially cold water, room temperature water, because you got a lot of hydrocarbon here, which is nonpolar. And this ain't going to like water, because water is pretty polar. So a relative question versus an absolute question. Very often we'll do relative comparisons. Okay, which one should be more soluble in hexane? Just plain hydrocarbon.
Probably the second one, but not very much.
Which one more soluble in hexane, which is nonpolar hydrocarbon?
Second.
This one. Because the more hydrogen bonding you see, that's because there's more polarity. Because the NH is a very polar bond. That's why we're able to say it's hydrogen bonding. Where the N carbon is not as polar. So more hydrogen bonding means more polar. Less polar is going to like the less polar solvent better. Because like dissolves like. Making sense? Okay, there's a list of some solvents down here. This is at this point for reference. You need to start getting familiar with solvents. You do not have to memorize every one of these for test 1. But if you're interested in learning the art and organic chemistry, I would recommend you start to learn these. These are some of the most common, at least in my opinion. I have classified these first. First off, you've got water, and then you've got organic solvents. All right? Non-organic, organic. Organic solvents can be divided into polar and non-polar. These are polar on this side, these are non-polar. But hold on. That looks like a polar molecule. Dipole, it's nothing to cancel it. Why am I calling it non-polar? Because this is based on being soluble in water or not. These are all completely miscible with water. A very polar
compound, these completely mix with it. That's why I'm calling these polar.
And most organic chemists do use this type of classification.
These over here do not mix with water. Even though that's a polar molecule, it does not mix with water because there's also hydrocarbon here. Polar molecule, but it doesn't mix with water. So it's not that polar. And in my scheme, I'm calling it non-polar.
You got to be careful when you talk to someone. You go out in the hall and you say dipole is non-polar. Somebody's going to say, what do you mean? It's got a dipole. You'll have to explain what we're doing here. It's not that polar. You can say, yeah, but it don't mix with water. So,
So why is dimethyl formamide soluble in water but ethyl acid stated?
okay. Guess what?
If you take this N carbon off right there,
That's soluble in water. One more carbon,
That's just it, that's just that one.
it's enough to make it nut. Very fine line. Okay, let's see where we're at to finish up and what we need to do to prepare for next time. Basically, we're going to quickly finish up this handout. We'll talk a little bit more about water. Is water good for anything? We'll introduce the idea of extraction, but this will be more in the acid-base handout, which will begin on Monday. Acid-base, hugely important. There's also a variety of miscellaneous things. Hopefully this is relevant and makes it all worthwhile. Why are you taking this class? So we can understand some of these miscellaneous things. Including, you know, what's that, Crestor? Crestor interacting with the enzyme. Okay, please be prepared, and we will have a quiz next week. Happy birthday to